So today, we're talking about programming security. Yep. Those of you who are having a nice calm experience during networking because you've already taken the networking class, you've just switched with the other half of the class that was required to have actually taken anything in operating systems. So operating systems half maybe will have a calmer day today as we do a crash course in how memory works. Oh, this is what I had as news last year. Britain really screwed up and they didn't have any food on the shelves because of a cyber attack. It's a fascinating one to look up. Why are programming languages so bad? There's so many answers to this, but I'm going to start with just a very fundamental concept to kind of help you understand how we got here, because, oh my goodness, especially when we talk about C. When I was a little kid, about 10 years old, I programmed this nice sleeping bag for my dog. Isn't it cute? It's got a little train on it. I'm not that old, but I coded this in punch cards. Knitting machines are coded in punch cards. See the little punch card over here? It's not very hard to understand. If there's a punched hole, it's black. If there's not a punched hole, it will be pink. End of description. I can think of several attacks to this. Like, you could really muck up this machine if you punched every single hole, for example. But the operator, who's maybe only 10 years old, actually has a very in-depth understanding of this machine because it is not very complicated. It's a fairly simplistic machine, honestly. It just knits where there's a hole or not. Attacking this is very hard because the programmer, even a novice programmer, has full understanding of their systems. And this is how it used to be in computer science. I mean, a long time ago, back when my mother took programming. And yes, my mother took programming because it used to be a field run entirely by women. At that point in time, you understood your full software stack because there wasn't much software stack. So things like Linux and C were all written under the assumption that you understood your full computer. By the way, this little drum here from the Computer History Museum, that is all the code for the computer. It has been literally physically written on, and it doesn't change. This is hardware before we had software. That is not how modern programmers work. As much as software engineering doesn't believe it, we have injected a mountain of usability into the side of software engineering. You now all approach software engineering just assuming someone else is going to sort out the lower stacks. Most people start, and maybe they program an application, they never even think about what's sitting down below them. And this is how modern programming works. We have a lot of problems, though, because often we start treating software engineers as if they have a full understanding of that stack, when they do not. And this has just gotten worse with AI, much worse. I've read some papers recently talking about why it's worse, which is actually really fascinating. They see statements like the programmer says, oh, please make this thing. And it makes it secure, but it requires like 20 libraries and for you to set up some sort of certificate authority thing. And so the programmer says, rewrite this so that it doesn't have the certificate authority. And the AI helpfully does that. And this is how we get horrendously insecure code out of AI. Because someone doesn't necessarily understand all of those components. We no longer have a full understanding of the stack, of everything that's going on. And this is where a lot of the problems come from when we're talking about software engineering. Okay, I think I rewrote this like 4 times, and it used to be security and privacy, security trust. I don't even know what the section is supposed to be at the moment, but it's a high level. You've seen this already, right? The star, square. Security really expects a specification. Who's supposed to be doing what? And you have to be able to say that. Because if you can't, I mean, how are we supposed to know? I'm not going to actually do this as a think, pair, share. I think I had it in past years and it was a nightmare, but I am going to put it out there to get you to really think about what I mean by this. How secure are the images on your smartphone? You take pictures with your smartphone all the time. You may take pictures of sensitive things. You may take pictures of passwords. You may take pictures of other stuff. How secure is that? Well, actually, the correct answer to this is, what do you consider to be secure? Do you consider all of your images uploaded onto Apple to be a secure thing in that you won't accidentally drop your phone in a pond and lose all your photos because access is a part of security? Do you trust Apple? Do you trust the code that's sitting on there? Do you trust Android? Do you trust the various device of apps that have all said, can I please interact with your file system when you set them up? At which point they may have access to your photos. My point here is that what is and is secure is heavily dependent on your trust model. And this is one of the reasons you see me pushing threat models a little bit more this year, because threat models have a big impact on what's secure. It's you're defining what you're dealing with. I'm going to make this point as well to start here. There are errors and there are flaws. We see both of these in security, but they are dealt with differently. So an error is by definition unintentional. No one meant to do this. It was an accident. Someone hit the wrong button. Error, unintentional, it's a mistake, it's a typo. And you can find it through testing. And you can find it through testing because here's the spec, here's what was built, and they don't match because it was an unintentional error. And you can only detect an error after it's been coded. So you couldn't have detected this error before you sat down at the keyboard and started typing things out. Compare that to a flaw. Code is intentionally written the way you're looking at. So think about my example a moment ago with AI, which you're like, please code this thing. And they're like, oh, certificate authority. And you're like, please remove the certificate authority. All right, we haven't even finished coding yet. We've made an error. Or made a flaw. Now things get a bit fuzzy, but that's a flaw. Something where when you were designing the code, when you were standing at a whiteboard kind of approach, and you're planning out your system, you've already made an error, this is a flaw. Flaws are intended design. You sat down and you intentionally built it this way. Maybe you shouldn't have, but you did. And they're impossible to find through testing generally. Because here's the specification, here's the code, and they match. AI is starting to help better in this situation because the AI will not necessarily test your code against the specification. It may also test it against known common weaknesses. And that is an improvement AI is bringing. And this one, flaws can be detected at the project planning phase. So I'm going to start in here. This is a famous example called go to fail. This is an error. Straight up. We found the developer who did this. I think he did it over Christmas break on a Friday. I don't remember exactly when he did it, but it was a really inopportune time to decide to push code when no one else was really paying attention. Can you find the error? Because what it does effectively is it turns off SSL verification. And this bit of code here was running on Apple for over 6 months on all phones. Found it? I'm just getting you to look at it for a moment. Think of it like a developer. How does if-else statements work? Or no, sorry, this is a struct, isn't it? No, this is an if-else. It just has to do with how the language functions.
Oh, goodness, else, that would look fine.
Yeah, if it had an else, it'd be fine. Our line is right here. This is called go to fail for a reason. Go to fail. What happens? There's no if. What happens if there's no if? It'll always execute every single time. That means that this line down here will never execute. The next line. As a result, the certificate validity is never checked. And 18 months. Almost every single Apple product for 18 months was not checking SSL certificates because this open source library got a pull request at somewhere over Christmas break and no one properly checked it. This, though, is an error. We couldn't have detected this beforehand. This is a straight up just typo. Honestly, he copied something and moved it to a different part. He copied the if part. He failed to copy the go to fail, left it behind, and this caused the issue. Okay, that is a fail. This is a flaw. Admittedly, I have pulled this off of a capture the flag because it is intentionally bad, and it's hard to find these ones in the wild because most people aren't that bad at it. What you're looking at here is a page source. When we did authentication and access control, you learned about a reference monitor. All authentication should go through the reference monitor. You should always check if someone's authenticated, and it should be the operating system that decides if someone's authenticated. And in this case, they're doing client-side authentication. Oh my goodness. So what they're basically saying, collect the password from the website, Here's what the correct password's supposed to be. Double check if it's true or not, and then send it through. Don't ever write the admin password in your website code, ever. But you wouldn't do this if you hadn't already planned to do the authentication client side, right? You actually have to work with two code bases to pull this off, because you have to work with the server code base and the client code base to make sure that the messages being sent back and forth are accurate. And then you've probably tested this a few times to make sure you haven't screwed it up. This is intentional. This is someone who hasn't really thought about what they're doing, but this is not a typo at all. And if someone had drawn this on a whiteboard system diagram and said where they were doing the authentication check, you could have identified this all the way before the code was written. Okay, so I'm just trying to pull apart human error from intentional design decisions as we're kind of moving forward into some of this space. This is the OWASP top 10. I checked this morning. They have updated since last year. I know it says 2025, but I think that's like November 2025, so this is actually pretty close. One of the things OWASP does is every, 4 or 5-ish years, it goes through and it tries to figure out what are our biggest causes of problems. And I am sorry to say that some of the line items here are incredibly stable. My slide decks go back to, I think, 2014. And you'll see some of these persist consistently. Some of them have merged, some of them don't. I think. First thing on the list, broken access control. You're just not checking whether or not someone is authorized or not. And this one's so simple, I usually don't bother teaching you in class because it's kind of obvious. But it is still the leading causes of problems. Cryptographic failures actually had a weird thing. Cryptographic failures also is inclusive of identity management. So knowing who you're talking to across a connection, because we've moved from a state from not. We used to do that separately, and now we almost always do it via cryptography. So it's now in the cryptography. But look at how few things vanished. And things that did vanish, so like here's server-side request forgery, which we'll go through not today. Has moved up into broken access control, which is true. So sometimes they merge. But most of the things did not fall off the list. And if I go backward in time, oh my goodness, look, broken authentication is living right there. Injection's still here. Where'd injection go? Did it end up moving? No, injection. There's injection. You'll see them kind of describing things occasionally, but injection, broken authentication, security misconfiguration, those are all happily still there. We roll all the way back to 2013. Oh, look, injection, broken authentication, security misconfiguration. I am sorry to say that the root causes of security breaches are pretty consistent across time. And keep in mind that these are the high-level conceptual issues, right? These aren't the low-level bugs. The low-level bugs are changing all the time.
What is this list? Like what's the description for this list?
So OWASP is I don't know what OWASP does. The only reason I ever interact with OWASP is this list. They're a software engineering group. They do a bunch of things. One of them is they publish these lists of vulnerabilities and long descriptions of each vulnerability, the causes and the ways to correct them. This is considered one of the top things a security researcher should know about, or a security professional, and try to avoid, is things on this list. And they maintain it periodically. So they go through, again, I forgot to look up how they're actually doing this morning, but they're clearly pulling code base and doing tests against them. And they're doing tests against common weaknesses, which fall within these categories. So they take a bunch of commonly known weaknesses, they categorize them into these groups, and they look at how persistent they are across the last couple of years. And they use this to figure out what are the things that are causing all the problems. Which is another way of saying, what should this class be teaching about? Because it's actually quite important and it's causing problems in the real world. And you can pull up OWASP. If you just pull them up, OWASP top 10, for every single one of these, it has in-depth descriptions. All right, that's my high-level crash course entry into secure programming. I'm going to take you through a couple of the most common things, a big one being buffer overflows and buffer overreads, because this is just the cornerstone of why won't it go away. And it's also much easier to understand. This is probably the easiest part to understand this space. Past that, bluntly speaking, there are so many ways to muck up a computer. Networking, at least we're all limited to the TCP and IP protocols, and I can teach you those because that's the root. But oh my, there are so many ways to muck up a computer. So a lot of this section is actually just going through famous stuff and getting you to open your mind up about just how many ways an attacker can get into a computer. So a buffer overflow. So the idea here is that, I was expecting another slide, so I'm just going to come over here and just make sure I'm not lost. Okay. I put the in the call stack section, and I'm sorry, I'm just going to hop ahead very briefly because I've been trying to write threat models down first. So I'm sorry, I've hopped the call stack section, and I'll hop back again. The threat model we are talking about when we talk about things like buffer overflows, and most of this section on secure programming, is that we are assuming an attacker that can cause code to execute, so code that was already existing on the machine, so not code they've added. Code can cause code to execute, and they can control some of the input values. I think I've just described a web server. Any situation where a user that's potentially low privilege, and we're just assuming low privilege for the majority of this, so they don't have a lot of access rights. And they can only cause code to execute that a user at their own privilege level has the ability to do. So this is a limited user. And they can't do anything else in the system. They can't just inject a file. Now this will change as I keep talking, but for this section, we're specifically talking about this. This attacker might be a man-in-the-middle attacker. So maybe they have taken a legit user and injected some stuff in the middle. Maybe this person is a random person on the internet who's just poking at a web server, because the moment you open a web server and enter a bit of content and hit enter, you are this level of attacker anyway. You're not an attacker usually, but you have this level of access. Low privilege, legit, but problematic user. So sometimes we call this benevolent but curious. So someone who is a low privilege user and just wants to, well, what would happen if I hit this button? Or a compromised legitimate user. So a user who has fallen for a social engineering attack, given up their password. And we hope that that person is low privilege. So this is our threat model. All right, hopping back to the buffer overflow. So the idea of the buffer overflow is quite simple. We write more data into a buffer than is the size of the buffer. So if you spent much time in software engineering, especially if you're coding something like C, it starts demanding to know a lot of things. It wants to know how long is your integer, how many characters is your string. If you spent a lot of time coding in Python, it's all helpfully hidden that from you. But the lower the level the language you get to, the more likely it is that it starts making you specify the exact size. So these examples are in C because C is an awesome way to shoot yourself in the foot. And it's also a great way to actually do more low-level control over different elements. So if you know what you're doing, this is great. And if you don't, it's a good way to create a lot of security compromises. Some C things just cannot be used safely, period. So imagine we have this very simple little code up here. We have a character string that's called A, and it's 8 characters long, and it has nothing in it. And we have an unsigned short B, which has 1979 written in it. Here what they look like in memory. Then I use some horrendously insecure command called string copy, in which I take A, and I copy the word excessive into A. Well, excessive is longer than 8 characters. So what happens to the last couple characters? Well, it helpfully just starts at, well, okay, first off, in C, A is it points to the front of the array. So it just helpfully takes E, X, C, E, S, S, I, V, E. Or is it just E that goes right here? And it helpfully overwrites. I know, shocking. That's all of a buffer overflow. We've now learned buffer overflows. I have a lot more to say on the topic, but that's it. That's all it does. It just means that you have written over the end of the buffer. You didn't double check the length of your array. C is one of the reasons it's so dangerous is it frequently just allows you to do this without double checking the length of any of the variables. A buffer overreads the same concept, but we're reading instead of writing. So here we have our exact same two variables. And down here we do char overread. Okay, there's a lot of C in here, but basically it says read the length of A plus 8 characters. Or plus 8 bytes, sorry, 8 bytes. Now it will read out all of the values. Oh. Okay, I should have used the previous blank version, but it will helpfully just read out all of it. Which means that now we know what was in that value, what's in that unsigned int is now available to the attacker because they were able to read more than they should have. This is important if the blue section is maybe available to our low privileged attacker, but the yellow section was not. Right now I've assigned both of these variables in the same program, but what happens if they're not in the same program? So you have to start thinking about how memory is organized within a computer. Because up till now, you've always assumed, that my variable's in my variable position, and then we don't worry about it. But what's sitting before and after your variable? The most common or famous example of this is something called Heartbleed. This is an XKCD comic about Heartbleed because, bluntly speaking, this is the best description I have found of it, and he's quite good at this. So the way Heartbleed works is Heartbleed is an attack on a web server. I mean, you could make a standard computer web server, but it's an attack on a web server. So on a web server, sometimes you want to do the equivalent of ping. So you basically want to say, are you up and alive? But rather than just saying, are you up and alive, I want to know whether or not your memory is functioning properly. And so what I do is I say, I do what's called a heartbeat command. I say, here's the word, what did he use? Bird. Here's the word bird, 4 letters. Say bird back to me. And then the server responds back bird. This is trivial, right? So you see the little character here sitting there going, okay, so what I'm going to do is I'm going to say potato, 6 letters, and it helpfully goes and says potato, 6 letters. So what does it do? It writes potato into its memory, and then it reads the 6 letters. Then I say, okay, well, can you do this with then it reads potato back out again. It reads it from its memory back out. And it has to do this because the main point of this is to check how functional the memory is. So he tries again. Okay, let's try with bird, 4 letters. Bird, 4 letters. He has a bit of a think. Hat, 500 letters. Now it reads out hat and all the rest of working memory. Now, the working memory of the server, what access control level should this be at? Really high. What are things in the working memory of the server? Maybe the private key? What would happen if I could just get the server to give me the private key? How many users is a server working with? Usually not one, usually a lot. So what about somebody's SIN number? That might be in working memory of the server if it's currently interacting with someone else on health data. There's a lot of fascinating stuff in the working memory of a server. And so this is the heartbleed attack, in which what we just do is we just do a buffer overread. That's it. And what was happening, that what caused this, is that, see this 6 letters? There is no code that says potato, is it actually 6 letters long?
So why would that protocol even allow people to specify the number of letters they want to reply back?
Because you want to make sure that the memory doesn't have an error. The whole point of this is the memory doesn't have an error.
Right.
I don't actually know the answer to your question is the short version.
Yeah.
My best guess is I don't know how old this code is. And the older the code, the more likely it is to say this is my array and this is my length. Because that's a very common thing to do in C. That's why. It's basically, I'm sending you this array, and this is the length of the array. And what should have happened is the server-side code should have taken that string and the length of the string and said, are they the same, and then progressed.
Okay, I was just curious about something like that string in the way it was being sent to the server was actually null terminated, because then it becomes very difficult to make sure that's reasonable. Really not sure.
I don't remember about the null termination, but it's kind of irrelevant because the problem happens. Yeah.
If we're trying to make sure the memory is intact, if the memory is intact, then the null termination can get lost.
I did not dig into any of those points. You are very welcome to pull it up. Heartbleed is a very famous example. Also, I'm sorry to say, I didn't click the slide. It is still helpfully running today on a shocking number of computers. Why? Have any of you got any smart devices at home, like these TV things or these kettles? Well, when you first plug them in, they don't have access to the internet, do they? This is so sad. They really want to do advertising. They'd really like to be connected to the internet. And so what does it do? It tells you in the instructions to connect your phone to the TV. How can it do that? Well, it has to run a mini web server, doesn't it? It has to run a helpful mini web server on that device. And it does a very small stack to do that because it just needs a small amount of interaction with your phone directly. But it's running a mini web server. Do you think anyone's pushing updates to it?
Hopefully.
A shocking number of things like Heartbleed are still running on small IoT devices because no one ever bothered to update them. And I haven't seen a recent search of it, but I suspect it's still out there. When I last looked, maybe 4 years after it was fixed, about a third of web servers were still vulnerable to it. All right, buffer overflow, basic concept. But we can't really weaponize it in the way I've described it very well. We weaponize it by putting it on the call stack. All right, we just did the threat model. Okay, there are many operating systems out there. There's many compilers out there. I'm sorry, I've picked one, we're running with it. So things like the order and the directionality of the addressing. Again, I've picked one, we're running with it. I'm aware there are other ones. But the main concepts we're still trying to get at are different. So like this has high and low addresses. All right, how many people in the room feel like they could describe the call stack to their neighbor? We're capable of describing what it does, the stack on a operating system. I'm not getting many hands, or at least I'm not getting a lot of high confidence looking. Okay, we're not wasting our time then. We'll spend time on this. It's okay. More than a third of this class is graduate students, which means I have no idea what education you had before you arrived, and that makes it very complicated. When you want to run a program, you need access to a pile of stuff. You need access to your own code. That's rather important. The compiled version, but I'm going to be showing you the version before it was compiled for all of our sanity. But you need the compiled version of your own code. You need the data you're going to operate on. So you need to know where that is. You need a space to kind of stash big stuff, and you need a space to stash small stuff. The heap is the space I stash kind of big stuff. malloc would be the command, so I can go and kind of allocate a chunk of memory. And the place where I do kind of scratch pad level stuff, we call that the stack. And we're mostly going to be attacking the stack in this space. The stack grows towards lower addresses. So the stack pointer, called SP here, it looks like it's going up here, but it's going down in memory address. So it's going towards the low address. Heap goes the opposite direction. So it starts at the high address at the bottom, and it slowly grows this way. And the heap starts at a low address there and slowly grows that way. And it's segregated from the data and the code. I took it out, but I used to have a thing pair share on what happens when they crash into each other. The short answer is the operating system does not let you do this, but if it does happen, you're in big trouble because you can overwrite things. So the way the call stack works is, here's a set of functions. We have main, we have draw square, and we have draw line. 3 functions. Each function operates by itself until it needs to call something else. So main over here is a fairly simple little mini function. It just calls draw square. Draw square takes in 2 numbers, calls draw line. Draw line then goes and creates this character buffer for educational reasons. Each of these creates what we call stack frame. So main has their own stack frame. Draw square, which is pictured here, has their own and draw line has a stack frame. So this blue here, this is the stack frame for draw square. This is the stack frame for draw line. As this program executes, we start here with main, which is kind of in the dots down there. When it calls draw square, the operating system creates a stack frame for draw square. And it uses those things, and I'll talk about that in a moment. When draw line is called, that teal thing up there is created to go and to handle everything involving draw line, and the stack pointer goes up. The stack pointer always points to the top of the stack. So when it finishes this character buffer, it will return. The stack pointer will jump back down to the top of this blue, because that is now the top of the stack once the function is completed. All right, it's kind of vaguely making sense. So the idea here is the stack is continuously maintaining things like this buffer, these variables. What's in each one is the parameters. So the parameters are the things that are being passed in. 1 and 2 here. Draw a line, this is 1 and 2, which are A and B. And then draw a line, which is also 1 and 2, which is also being passed in here as A and B. So 1 and 2 would be sitting here, for example. The return address just sends us back to where we originally called it. So draw square here is calling with 1 and 2. So 1 and 2 would be the parameters. The return address would be line 8, effectively, because it returns back here. And then a locals for draw square, which basically don't exist. But up here in draw line, there's a character buffer. Okay. I'm going to do that again with another simpler program. When a function is called, the calling function adds the function parameters to the stack. Here we've basically done the exact same thing as I showed you before, but now I've actually written everything in. So we have here a main function, and we have 1 and 2, and we have A and B. So what happens is it goes and it creates, down here at the high address, we put B in, and we put A in, and we put the return address. The return address returns us back to line 5. It has to return us back to line 5 and not to line 6, because what if this had said func12 plus 3? So it has to return back effectively to line 5. Again, this is a minor limitation that we're looking at not yet compiled code. In compiled code, line 5 would be many small instructions, and so it's actually going to pop back to the point in the compiled code. But it comes back to that point. And then above the return, we have everything that's declared within this function. So func here is declaring this buffer, and the buffer is sitting here. Okay. We are doing a think, pair, share right now, because if you don't get this, you're not going to get the entire rest of lecture. So 1 minute, I have added func2. What will the stack frame for func2 look like?
What pointer points to the highest address in the stack frame for func?
I do not remember, but I think this is an operating system set value. Because the position of the stack itself is something the operating system maintains.
No, not the position of the stack.
No, but it is the position of the stack. The stack is positioned between the start value and the top. These lines here are defined by the operating system. It decides where it wants to do that. So there's not a general pointer that states this. The operating system is maintaining this fact.
I'll ask after class.
Okay.
Just a question, why do you have the buffer at the bottom here, whereas for the example for func1 we had that on top of it?
Okay, if that's confusing, I will draw the full thing. I've abbreviated. This is just the answer I was looking for.
Oh, that's the other end.
But let me just kind of, okay, the buffer here is now too short because I ran out of whiteboard space.
Then it'd be the red AB, right?
So this would be a return to 9.
How's that? Yeah.
This is a return to 6, thank you. And then below this is also AB. So this is what our stack looks like right now. For function, so this is for func, and this is for func2.
I was just confused that there was no buffer for,
Technically, main also exists,
yeah.
but since main has no parameters and no values, it would be simply a return. And we don't know where it's returning to because that's not specified. All right, is everyone still with me? Okay. Buffer overflows aren't that hard once you understand how this addressing works, but if you don't, they're not going to make sense. So the goal of our attacker, our low-privileged attacker, is able to impact this A and this B because they're passing them in. Actually, this is kind of a bad example because this is hard-coded. But imagine main was taking these in. And I have an example later where they do. So the idea here is we want to overwrite the return address. So how is this thing working, right? If I go back, this return address is telling me what part of the code I'm going to go back to. The return address is mapping into this code. So what happens if I overwrite it and I point it somewhere else? This is called a stack smash. So the way a stack smash works, and if you do this, you'll either crash the program, maybe that's your goal, limiting access, or you can execute code at your new address.
When you say execute code in the new address, wouldn't that also assume that the program counter is tied to the stack counter in this way? Like you have to pre-write.
The program counter is not tied to the stack point counter, but the return address, which isn't on the screen, the return address is pointing somewhere in the compiled code.
Okay, so
It's the line that's currently being executed in the compiled code, the one you have to return back to. So your program counter is doing it for your current function, but you need to know what function to go back to. And so if we adjust that to where we'd like to return to, as opposed to where the programmer wanted to return to, we can do some fun stuff. So here's a hard-coded version. Don't do this. But imagine I have this integer buffer, 10, and then I just tell C, oh, I happen to think it's 20, and write the number 37 into it. And now what happens is I used to have this nice thing here that had return address and an A in it, but I've now overflowed it the exact way I described before, right? I'm writing down. Keeping in mind, we go up when we're writing in an array, right? So an array buffer would start writing here, because this is position 0 or 1, 2, 3, 4, 5, 6, and then come down here and just keep writing, because it's going to write down, or it's going to write towards the high address. So here's a rather simple fake program. Here we have this main function. Again, it's passing in 1 and 4. I don't know why, just because I copied it. And what it does is it calls gets. So what's happened here is we have this billing program we started, and it says enter serial number. And you enter this serial number. This serial number it's the correct length. I forget what I should put in there, but 10 characters. So what's happening here is that it gets the buffer. So it calls gets, which means get string, get something from the terminal, and put it in the buffer, and then print it. In this case, everything works fine because it takes 10 characters, it reads 10 characters in, and the whole program moves forward exactly as it's supposed to. What happens if the user does that? Now it calls gets. It helpfully just keeps getting the string until it's done. It does not check the end of the buffer, doesn't check the array length, and just keeps writing. And now we have a buffer overflow. Now, it will helpfully print out exactly what you wanted because it's going to keep executing here. And the return address is not important for our initial writing. So we're going to keep going down through here. We're going to do printf. We're going to print out the original buffer length, so first 10 A's. We're going to hit there, and then we're going to try to use our return address to jump. But now we're going to try to jump to an address that is defined as a whole bunch of A's, and we're, in this case, just going to fail. Because this address makes no sense. All right, now I found a way to write things onto the stack, and I found a way to change my final address. These both sound awesome. What do I do as an attacker? Well, maybe instead of injecting a bunch of A's, I start injecting some code. Because I can inject code, but you can write anything you want on a web page and hit enter. So I put the evil code on the stack itself, and then I changed the return address to point to my evil code. Because if I go backwards a bunch, this is one big chunk of memory, isn't it? It's just a whole bunch of different addresses. And if you're thinking, oh, wow, I can do this, the answer is modern stuff will not let you do this.
Oh, yeah, so that's what I was going to ask.
Yeah, I figured.
Because the modern one separated out the instruction memory from the actual program memory, right?
Sort of. I will get there. Yeah. So a lot of stuff I will describe today, modern operating systems will not let you do. We have learned to check for this, but this is the starting for how we cause a lot of trouble. So the idea is we just overwrite evil code. We overwrite the return address. It's all an address. So we just point back there, and now we can run our evil code that we implemented, even though we shouldn't be able to run code on this system, even though we're a low-level attacker. This is bad when this happens, because this means that you can do arbitrary code execution, because what level of authority does the processor have? A lot. Where was the access control check probably done? Before we even ran this. So before we even started running this program over here on like void main, an access control system probably went in and said, oh, should I be running void main? And it probably said, well, yes, this user is totally allowed to run this low security program. No problem. And sent it through to the operating system. Now, there's some exceptions to what I've just said, but I will get to those. And they mostly happen because this happened a bunch. And then we learned to fix it. Okay, so how can we do this? So first off, this doesn't work as neatly as I've just described because you're kind of going in blind. Where's the return address anyway? How many variables has the programmer put there? Maybe you can figure that out if it's open source. But a lot of times, particularly long ago when we didn't have the internet, where we didn't have a lot of code shared, you didn't know what was going to necessarily happen. So there's some neat tricks you can do. One of them is you could just make a bigger target. What happens when a computer gets a no-op? No-op means no operation. It means it just falls to the next address. So one solution is to just write a huge pile of no-ops. So here's the overwritten buffer. The overwritten buffer is predominantly no-ops, followed by evil code, followed by a whole bunch of return addresses that all point back up somewhere up in here. Now, if you're off by an address or two, it doesn't really matter because what happens is we write a whole bunch of return addresses. This is the real return address. The real return address has now been overwritten to point kind of somewhere up here vaguely. It hits up here. It just starts no-opping, 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 run evil code. This allows the attacker to make a big target so they don't need to know the precise address. Just something close. All right. We don't want this to happen. This is bad. We don't want this happening on computers. So to stop it, we use something called a canary. The idea here is that here's the buffer, here's the return address, let's put a canary in the middle. If the canary gets overwritten, then we know that we have a problem and we just crash this program. And we don't actually allow the problem to persist. Canaries are named after canaries in coal mines. So canaries breathe much faster than humans. And as a side effect, if there's something bad in the air, predominantly gas, the canaries will get sick a lot faster than the human will. And this is a way to detect something you can't see. And this is what they're named after. They have these elaborate boxes for the canaries to make sure the canaries survive the experience. It's actually, if you read into this, it's kind of funny, like the sheer amount of elaborate work that's put into making sure the canary survives, even if they breathe in bad stuff. Anyway, we're doing this here. So the idea here is now if the attacker starts overwriting this buffer, they start writing down, they're going to overwrite the canary. What happens is now the operating system, before taking that return address, double checks the canary. It says, is the canary the value it should be? Keep in mind that it's possible maybe that the attacker will try to write the canary exactly as it should be, but it's actually really hard to do, especially since you need to know the precise position of the canary. A no-op won't cut it here. it won't be good enough. The computer will not accept one. It must have the canary in the exact right position. And the most common value for a canary is to use a null terminator, a string null terminator. So normally in a program, if you write a string null terminator, it assumes that user input has completed and will stop processing. So if you try to write the null terminator string over the top of the canary, maybe you'll succeed in writing the canary, but you won't succeed in overwriting the next part because the program will null terminate up the string.
So the value we're going to track things is written as an immediate value in all commands.
The operating system is checking the canary.
The operating system is checking.
So the operating system is in charge of putting all of these values here and all the values there. And the operating system maintains a pointer to the return address. And I guess in this case, it would also, I don't know if it maintains a pointer to the canary or if it just does some math off the return address. But it knows the precise position of the canary. So what happens is your program, it goes down all the way to the end of the function, and then it hands it back over to the operating system, and the operating system says, okay, now I need to go to the return address. It looks up the return address. It checks the canary. The canary is okay, then it jumps to the return address. If the canary is not okay, it has a massive fit and crashes your program. But a crashed program is usually better than reading out memory or running bad code. So that's usually how it's handled. There are many ways to handle it.
Is there any advantage in using a dynamic value per canary instead of using the same value for canary?
I have not dug into canaries enough, and there's better approaches that will come on the later slides anyway. I'm pretty sure we're using the same. We have an assignment from last year that's based on the Seed Labs that has you code some of this stuff in a VM. And we'll probably be doing that again this year, that we have to adjust for the way we're doing things. But the string terminator is kind of a simple thing. Again, we're looking at a Swiss cheese model here, right? Maybe you can get past that neural terminator through a different method, but now it's a little bit harder. This was brought up earlier. So we've been talking about access control thus far as access control for a person. And usually we're looking at, when we've talked about access control, we had a subject, which is usually the human, an action, and then the resource. This is very people-based, right? But we could also think of access control in terms of just the actions that can be performed on this at all. So one of the big problems we have in secure programming is code, and then there's data. And when you get the two mixed up, you have a problem. So what's happened here is that in a buffer overflow, we had data, the content of values, buffers, that somehow overwrote code, which is the location of where we're going. And we always want to keep code and data separate if we can. One solution to that is something called a no execute bit. So what the operating system can do is it can set a no execute bit on a whole bunch of spaces that are supposed to have data, namely the stack and the heap. And it can say, under no circumstances are you to use any return value that comes into these spaces, because these are no execute spaces. And we're not limited to just these. You can mark this in other areas as well, pages and whatever. I don't want to get too deep into operating systems. But the main point here is that this is set. This is also a form of access control. It's just done within the computer. And the operating system itself just says, yeah, don't execute this. This completely destroys your ability to do that thing where you wrote some evil code and then you pointed back to it. You can't do that anymore because you can only really write the sections that are data or the stack. But there's some nice ways to get around this anyway. The most common method is return to libc. So a lot of computers happen to have the library for C libraries somewhere in their systems because C is a very predominant language that is used extensively. So most computers have this. And most computers have installed them in a persistent and consistent location because by default, you put the C library in the same place on different operating systems. Especially since we're talking old stuff here. We weren't doing much variation at the time. It's very consistent. And so as a side effect, one thing is I could go and do my buffer overflow, but instead of overriding the return address with my evil code, I return it to a point in the libc library. Now you can just start coding with whatever libc function you'd like, and there's a lot of really nice libc functions out there. And yeah, again, and that libc function, okay, how that works is a bit complicated, but it would potentially work. This only works because the attacker can predict addresses. So it only works if the return address, the attacker is able to write a return address that is sensical. So keep in mind, I said earlier, you can go and write a return address, or you can use a buffer overflow to just crash the program. We can definitely still do. But if I want to use a buffer overflow to to run the code I want to run, I need to know what address to send it to. It was really convenient when I could go and just send it to my internal to the stack address because I knew where that was. But I have to know where this is. And one solution to this is just start randomizing it. There is no reason all of this needs to be one contiguous piece of memory. There is no reason libc needs to be in a physically consistent location. Computers are awesome at randomization, and computers are awesome at maintaining information about what is where. And so we turn on something called address space layout randomization. And the idea here is that we randomize key locations of data and processes, such as executable codes and portions of the stack, heap, and libraries are all in places that you wouldn't expect. So it's not necessarily the case that the stack and the heap go towards each other. And that randomization cut out a lot of security problems because it became very hard for an attacker to predict the addresses. All right, all of what I've described here. So we started early on with me talking about kind of high-level problems. Buffer overflow is an example of what we call incomplete mediation. And now we're pulling access control is now coming back into the conversation. Incomplete mediation is a situation where we just haven't checked the authentication, the access control, who is on the other side. We basically skip the reference monitor somehow. And so the attacker's goal is to get around the reference monitor. Access control probably sounded a bit boring when we went through it because your operating system does a reasonably good job at saying this user has access to this file at that level. So what the attacker is always trying to do is try to convince something else to give it access it shouldn't. And this is an example of that. This is an example where the attacker is basically trying to use the authority of the the authority of the operating system or the CPU to gain access to data, because it can access it, that the user did not have access to by overwriting the return address, and it's sending us to a part of execution that it wasn't supposed to do. The broader space is just, you're just trying to make sure, you're just trying to go around a reference monitor. That's mainly what incomplete mediation is. So for example, you have a client. The client sends all of this stuff. The last thing on the client thing it says is login equal true. All right, this is a good example of incomplete mediation. If I'm an attacker, what am I going to start doing? I'm just going to edit that, because on the server side, we have a function. It just checks whether or not login equal true. And then the user, charge user a certain price. Better yet, if price is on the list, was price on the list? Price is on the list, yes. I would totally change that too. Whether or not they're logged in, whether or not the price, this is an incomplete mediation, failing to check the authorization and properties of a subject object before using it. Buffer overflows happen deep within the operating system, so we don't always think about them this way, but this is what's causing them. This code I'm showing you here, never use this. In fact, a modern compiler won't even let you use this. It will throw a fit. But if you pull the old C books, they're like, oh, totally use this. Because this is dangerous. Gets doesn't include a length. You have to specify the length of the buffer when you created it, but you don't specify it when you read into it. This is bad. Modern languages don't even let you make these decisions. It just says, no, it shall be this length, put up with it, just to make sure this doesn't happen. Don't ever use this code. I don't remember why I put that there. Sorry, I removed the slide this slide is referring to, so I will ignore it a little bit. I'll kind of cover it, but I don't mean this. The odd numbering up there is there for a reason. When you're coding, it's really important to not assume trust. Like, make sure that something actually did change. Use an authentication mechanism that can't be bypassed. This is a good example of bypassing an authentication method very easily. And define an approach that ensures all data is explicitly validated. So when data comes in, do not assume that it is the correct length. You need to make sure the server tried check. A key to hacking is frequently just asking, what if? This wants a date. What happens if I enter a name? This wants a date. What happens if I enter a negative number? This wants one thing or another. What happens if I just send something a bit different? You see a lot of things in hacking is just kind of questioning the edges of things. Or even doing things like pulling up on APIs and just scanning through them and go, do I have to actually send in login details for all of the sections here? Maybe not. A lot of things you see in hacking is just kind of testing these boundaries. All right, I actually managed to get through my slide deck today on time. I'm very proud of myself. Why did I go blank? All right, I also broke something. I don't know what it is. But that's okay. We're at the end. Thank you very much, and I will see you on Friday.
Yay.